Hello, my name is Dragos and I'm one of the authors of ElectroWay Smart Routing for Electric Car Charging. In this presentation, we present a real-world routing algorithm and the specific issues that need to be taken into account when designing such a system. The world is in the process of transitioning to more sustainable energy production and consumption methods. As part of this process, we are seeing the beginning of an exponential S-curve in the adoption of electric vehicles. The issue of creating long trip routes with the special characteristics of electric cars arises. A recent GUI report, which included a survey of more than 5,000 people who were considering purchasing a car, shows that two of the main concerns people have when switching to an electric vehicle are the driving range and lack of charging infrastructure. Since electric vehicles adoptions has only recently started to gain traction, the general ecosystem is still seeing high variance in specifications and standards. The existence of multiple types of charging connectors, car charge capacity, charging station capacities, and wildly different car ranges introduces complexity for electric vehicles car owners when having to plan trips or daily commutes. These tasks can be completed by humans fairly easy, but it requires them to invest a sizable amount of time to search and compare various charging stations along their routes to estimate and compare which option would lead to the least total route time. Another consideration, especially for people interested in buying an electric vehicle or who have just recently bought one, is the worry of running out of power before reaching a charger. While charging infrastructure is seeing a lot of growth and seems to only be accelerating, the fact that electric cars have smaller ranges and their efficiency can be severely impacted by many factors such as temperature, speed, wind, rain, and snow, or the use of internal system, it is often the case that the manufacturer's estimated range is inaccurate. This can further complicate the process of planning a route for drivers, since if they don't know of these implications, they might overestimate the distance they can reach before running out of power. There are also practical aspects of actually using such an algorithm in the real world, such as the time required to calculate the route and the associated cost of the calculations. In the case where we want to externalize the storage and maintenance of raw data to Google or TomTom, our costs will become a function of how many point-to-point route requests we make, so such an algorithm should also try to minimize these costs. To address this problem of optimizing the planning of routes, specifically for electric cars, which tries to take into account various real-world factors, we propose a simple, efficient, real-world usable routing algorithm which leverage existing maps and routing services to offer a routing service at low to no cost. We pack this algorithm in an Android mobile application named ElectroWay, which offers the additional features of letting users add their own charging stations in the system. The application is given a car object containing relevant data such as maximum electric energy supply, charging speed, maximum speed of the vehicle, and so on. It will also receive the geographical coordinates of 2 points representing the starting point and the ending point. In case of the need to recharge the car battery, it will have access to a collection containing charging stations object. Each object contains relevant data, the location of the station, and its charging points. To determine the route between 2 points, we use TomTom, a mapping API that generates routes without considering the collection of stations or the fact that the car may not be able to follow the generated route due to insufficient energy level. In addition to the generated route, the API also provides useful information about route length, travel time, and consumption. We use OpenWeather API to find out details about the weather conditions. This way, we can estimate how the external factors impact the output. This is done in the data processing step, where we calculate how temperature, wind, and the route conditions affect the consumption. Given that the application is facing a real-world problem, large input data, and long response times from external APIs. It will use a heuristic approach in order to produce a satisfactory solution in a feasible amount of time. There are two cases. The first one, the car can reach the final destination from its current location without having to charge. In this case, the route offered by TomTom, along with the information related to it, will be returned unchanged. The second one, the car cannot reach the final destination with the current energy level. In this case, an intermediate point will be sought, a point at which the car will stop to recharge. At each step, it will check if the destination can be reached by making a request to TomTom. If it cannot be reached, a convenient station will be selected, convenient in terms of time and distance from the current location. This station will become the new current point, and the whole process will be repeated until the car is at a point from which it can reach the final destination. Initially, we will request an initial route without considering the car. The stations as close as possible to this initial route will be selected, so that the calculated route is as close as possible to the initial route. Therefore, we are looking for a point that can be reached, a point on the initial route as far away as possible. The generated route is an array of geographical coordinates. A recursive binary search will be performed on that list. Successive requests will be made to TomTom to check if the geographic point in the current index is reachable. Because the requests are time-consuming, we will limit the depth of the recursion. When the preset depth has been exceeded and an accessible point has been found, then it will be returned. For example, for this case, we try to find that reachable point. As shown here, that point it is not reachable, so we'll search for a closer point on this part of the route. As I said, if we exceed the depth limit, we'll stop and return the latest accessible point that has been found. Otherwise, we'll continue the search in this part of the route. In the next stage, all the stations that the car can reach will be extracted. A tree map will be created in which each station will have a corresponding total time and distance tuple associated with it. The total time is the sum of T1, the time required to get from the current point to the point determined in the previous stage, T2, the time required to get from the point determined in the previous stage to the final destination, and T3, the time required to recharge the car. This tree map will be sorted in ascending order by total time. This will give us a list of the most convenient stations in terms of time. Because there may be a station that is most convenient in terms of time, but that it is too close to the current point. In this way, stopping too early without the need to, we need to select stations which are further away, but that don't increase the total time too drastically. This way, make sure we don't stop too often. This new station should not have a much larger total time than the most convenient station in terms of time. In order to do that, we sort the original tree map in descending order by distance. We will iterate through it and return the first station whose total time is less than 10% higher than the most convenient station in terms of time. After the station at which the car will stop to recharge, the location of this station will become the new current point and the whole process will be repeated. An improvement would be the use of caching. Create a graph representation of previous routes which were calculated by clients and store them in our database. When we have a new request, we first try to use the points and distances between locations already in our database and only request a new routing distance information when we need to. If the final routing distance time we calculate using our cached information doesn't match with the TomTom routing, it means we have to rerun the algorithm without using the cache in order to update it. Another improvement would come from integrating the ElectroWay application with existing charging station networks. in order to populate the database with more charging points so that we can create realistic testing scenarios. That was the presentation. Thank you for listening.